Namaste viewers, welcome to our technical channel Ganesh Piping. It is very important for us that you subscribe to our channel because I have seen the channel analytics and around 20% of the people are our regular subscriber. That means the 80% of the people are only the visitors, which is not a good sign because we consider you as our viewer family. So you subscribe us and support us because when you support when you subscribe our channel, it is a great help for us and a motivation for us to continue with the informative videos which are useful for the professionals. So now this is the final episode for the piping materials engineering. Before we start this video, you can support us by financially for which the cost of which will be utilized for the content creation and the video production. And now there is a phone pay link which is being mentioned in the description of this video. You can also, if you have not seen the previous episode of this part 1 of piping materials engineering, then we have shared the description, we have shared the link of that in the description. So do visit that before you start with this video. So now here quickly we will go through the important calculations that are associated with the piping material engineering activities. So the first and foremost of that is the pipe wall thickness calculation. In earlier video, we have seen that the piping wall thickness is the first activity which is undertaken at the start of the piping material specification or developing the PMS. Then second one is the PT rating, that is the pressure temperature rating. So what is pressure temperature rating? Like for example, if we have calculated the thickness of the given pipe, then we have to also identify the flange which will which is corresponding to that given thickness, and flanges are never classified based on the thickness, they are classified based on the rating. So we have to draw something common uh, which will be suitable for the given pipe thickness, calculated pipe thickness. Say calculated pipe thickness is say 16 mm. So we have to identify the rating for that. So that thickness is identified based on the pressure and temperature. So based on the pressure and temperature, we arrive to the rating of the flange. Then the third one is the RF pad calculation. RF pad, as we know that whenever there is a stub on stub in connection, we have to create a drill. We have to produce a drilled hole in that. So when the hole is drilled, there is a loss of material in this area, and because of the loss of material, the pipe section is weakened. So to compensate for this weakening of pipe, we have to substitute it with an additional material, and that is called as a reinforcement pad. It is a plate actually, basically we can see here this plate, and this plate is welded on the branch side, and because of this welding and this material of the reinforcement pad, we are strengthening the branch which is suffering from that loss of material. So lack of strength due to the loss of material. So that is the RF pad calculation. Then we have the line blank calculation for the given temperature and pressure. So now we will quickly go and see that how these calculations, some of the calculations we will see, not all is possible. This is the most important, that is the wall thickness calculation. T, we have to arrive at T. T is the thickness. Okay. And this is the formula PD divided by 2 bracket SE plus PY bracket close. The calculation is applicable for thin cylinder and shell. So what is the thin cylinder and shell? when the thickness is lesser than the 1/6 of the D. Like for example, if the diameter is 600 and 1/6 of 600 is 100. So if the thickness is less than 100 for that 600 dia pipe, then it is a thin cylinder end. If it is greater than that, then it is a thick cylinder end. Okay. So whichever will follow this rule, then we can use the, for thin cylinder, we can use this formula. So T is the thickness of wall thickness, pipe wall thickness. P is the design pressure applicable for pipe. D is the outside diameter of pipe. C is the corrosion allowance. So these are all the different terms associated with that. S is the allowable stress corresponding to maximum design temperature, and it can be identified from the table A-1 in ASME B 31.3. Because we are considering the process piping, that is why it is 31.3. So if you are doing this calculation for the power plant, then it will be 31.1. At the end of this session, we have given a comparative study between the ASME P31.3, that is the process piping design code, and versus the power piping design code, that is ASME B31.1. Then comes the E, that is the longitudinal joint efficiency factor, depending on pipe manufacturing process applicable for given pipe, that is ASME 31.3, table 302.3.4. Then comes Y, that is the thickness correlation correction factor, refer table 304.1.1 in ASME 31.3. Then comes the mill tolerance. So all this we are going to discuss it now. Just to give you a broader idea in a broader sense for the pipe wall thickness calculation procedure. First is to calculate the thickness to withstand the given pressure, and that is being calculated from the formula which was mentioned in this earlier slide. So as soon as you arrive to some values, you have to add a corrosion allowance. That corrosion allowance is what? Corrosion allowance is the extra thickness which is given to the calculated thickness, because the life of that plant is 20 years or 7,000 cycles. So during the 7,000 cycles, heating and cooling, or the 20 year, whichever is lesser. So during that, this plant should be capable to have the same capacity, should be capable to take the same load after at the 20th year. So that is why there will be definitely some corrosion associated with the pipe, and the thickness will keep on reducing because of that. So to compensate that loss, we are giving the corrosion allowance, that is the extra thickness. Then there is something called as a mill tolerance, which we have to add, which is 12.5% of the extruded pipe, and zero point 0.3 mm for the plate fabricated pipe. So what is this? Like for example, after adding the corrosion allowance, the thickness is 12 mm. So when you choose the pipe, it cannot be 12 mm. It should be higher than 12 mm, because due to the manufacturing process, it is not a machining process. It is a metal forming process. So because of that, this thickness, which is shown here as a wall thickness, is not a constant, because there is a waviness associated with that because of the manufacturing process, shortfalls of the manufacturing. It is not a machining process. Manufacturing process is the metal forming process. That is a ERW, EFW, that is the welding process. But how we form that pipe, that is not a metal cutting process. Machining is not involved. It is the some mandrel is being used for making that pipe. So of course there will be waviness in the thickness, and to compensate for this, we have to take the higher side, and that is the 12.5% we have to arrive extra. Okay. Then the step 4, select the schedule thickness from the appropriate dimension standard. For example, ASME 36.10 for carbon steel and ASME 36.19 for the stainless steel. If the piping network is stainless steel, then we have to go with the 36.19. Then once we get this thickness, we have to do the back calculation and check that what is the maximum MAWP with this thickness, arrived thickness. MAWP is the maximum allowable working pressure. Okay. So at that given design temperature. Okay. The bottom line of this is that whenever we design a piping system, highest the design temperature, if the pressure crosses the design pressure, then there is something called as safety wall. But suppose if the safety wall will fail, then what will happen? Whether the pipe will fail? No, pipe will not fail, because the next level of failure will take place for the flange, because flange is considered to be weaker than pipe. And of course the maximum allowable working pressure will be for the pipe will be greater than the flange pressure. So the flange pressure is lesser than the maximum allowable working pressure for pipe, but it is greater than the design pressure of that pipe. So this is very important. So the highest pressure which it will be the MAWP for pipe, that is the pressure at which the pipe will burst, it will be the highest. So there should not be any bursting of the pipe. So the second level will be the flange pressure. So first the flanges will fail, there will be leakage to the flange. So that is the flange pressure, and after that we have to design the system for the design pressure, which is the lesser than that flange pressure. So this is the bottom line philosophy. So this is a comparative study. So 31.1 is for power plant piping, and for 31.3 is for process plant piping. 31.1 is lower allowable stress values, because lower allowable stress values, that is why we get higher thicknesses in our calculation. Higher allowable stress values, that means it is inverse. The calculations as per calculation thicknesses will be lesser compared to 31.1. So use of FOS. FOS is the factor of safety. So that factor of safety is 4. So that is why the thicknesses that are arrived are on the higher side. And use of factor of safety is 3 for ASME 31.3. There is no such limitation in power piping wall thickness calculation. And the equation for 31.3, the equation for pipe wall thickness calculation in 31.3 is valid for T is less than D by 6. So this we have discussed. Does not provide any such rule for pipe material below minus 29 degrees Celsius. This is not applicable, because when there is a power plant, thermal power plant, higher temperatures are expected, and minus 29 is a sub-zero temperature which can never take place. So by the way, minus 29 degree Celsius to 427 degrees Celsius is the operating range for carbon steel. That is why it is given minus 29. Provides extensive rule for use of material below minus 29 degrees Celsius. That is the cryogenic materials or the low temperature material. I will not say cryogenic. So that is the LTCS, which is from minus 29 degree to minus 45 degree, and from 45 degree minus 45 degree onwards till minus 250, we can go ahead with the stainless steel. So in stainless steel there are different grades, so that we are not going to discuss now. Is generally designed for 40-year or more of life, service life. That is the power plant. And this ASMEB 31.3 is normally designed for 20 to 30 years of service life for that process plant, and provides specific equation for PSV reaction force calculation. Code does not provide specific equations for PSV reaction for force calculation. So that's all about today's session. So thanks you once again for watching these videos, and once again I request you to subscribe our channel and share this valuable information. And also, one more announcement I would like to make, that we provide corporate trainings at affordable rates to the companies, and also provide training to individuals. There are online training available, and you can take advantage. It is at very lesser cost compared to the offline training, and the efficiency of that online training is also never compromised. So it is a one and one live session. So thank you once again, and keep watching our channel.